Our objective for this lesson is to be able to tell me what polar bonds are and how they differ between polar bonds and polar molecules. How polar bonds are different than what polar molecules are. Polar and non-polar bonds. Remember, we talked earlier about a non-polar covalent bond and a polar covalent bond. How could we distinguish the difference between a non-polar and a polar covalent bond? How did you know? How do you know? Do you know? What do you think? Go ahead, Mason. The difference in electronegativity. Excellent. So go ahead and take out your periodic tables. We're going to be using those a little bit today. The difference in electronegativity. So, as we looked at the polar and the non-polar covalent bonds, I always think of this as a tug of war. Okay, a tug of war. We are pulling for those bonded electrons. If it is a non-polar covalent bond, nobody's winning the tug of war. The tug of war is pretty even. However, if it is a polar covalent bond, then one of those elements is winning the tug of war. Somebody is pulling the electrons closer to their nucleus. Let's look at a hydrogen chlorine polar bond. Okay? The unequal sharing of the electrons. We talk about with these in covalent because, once again, the electrons are being shared. So in a covalent bond, we talk about partial charges. Now, when we dealt with an ionic bond, the electrons were being transferred from one substance to another. So we had the sodium just giving up electron to the chlorine. Okay, so those would be full charges. On these polar covalent bonds, we talk about partial charges because it's not 100% given away. So it's tough to see up here, but we can represent these a little bit different, a few different ways. And this little sign here, and I'm going to draw it big, gives me a partial negative there and a partial positive there. So those are the signs for the partials. Okay, the partial negative, the partial positive. So if this were the bond between hydrogen and chlorine, here would be the chlorine, here would be the hydrogen. The chlorine would be pulling those electrons closer to its nucleus based on the difference in the electronegativity. In a nonpolar covalent bond, there is an equal sharing of the electrons. Okay? An equal sharing. So in my tug of war, nobody's winning. Nobody's winning. If we look at chlorine, okay? Chlorine's a diatomic molecule. We hit briefly on the Super 7 yesterday. If we look at chlorine and chlorine, obviously the electronegativities are going to be the same, aren't they? So, is anybody pulling those electrons any more than the other? No. So it is a tie. That would be a non-polar covalent bond. So just a little bit of a breakdown, okay? A little bit of a breakdown. If we have an ionic bond, and these X's represent the electrons, the bonds. If I have an ionic bond, the positive ion gave its electron totally to the negative ion. This one would represent a nonpolar covalent bond because the two different substances are pulling at the same amount. Nobody is winning the tug of war. This one, the polar covalent bond, see how the electrons are pulled closer to this circle and away from that circle. That makes this side partially positive because it's losing the partial, and this side partially negative. Okay? Those electrons aren't in the dead center like these are. They're pulled over closer to one element than they are to the other element. Now, we talked about electronegativities. So once again, just to refresh our memories, we said that a nonpolar covalent bond was anywhere from 0 to 0.3 difference in electronegativity. A polar covalent bond was from 0.3 to 1.6. The ionic was 2.1 all the way up to 4. And remember that we had that gray area, the area between 1.6 and 2.1, where we had to check, okay, do we have a metal? It's ionic. Do we have a nonmetal? Then it's a polar covalent bond. Okay? So just reviewing our electronegativities. Now, let's look back at that bond between hydrogen and chlorine. Okay? Look at this. Now, I know these numbers aren't exact. I probably should change those. Okay? Because hydrogen's 2.2 on our periodic table, right? Okay? What is chlorine? 3 point what? 3.16. So they're a little bit different than what we have here. Okay? But nonetheless, if I look at the difference, okay, I take the 3.1 and I minus the 2.1 and I get a 1.0. That 1.0 falls in the range of the polar covalent, the 0.3 to 1.6. Okay? So I know this is a polar covalent bond. That's nothing new. We dealt with that the very first day we talked about bonding. Now, let's think about this. What's going to happen with this bond? Go ahead and do the math yourself and think in your head, what is going to happen between a bond of nitrogen and hydrogen? So, I look at the electronegativity of that, and what do I get? 0.84, right? What range does that fall into? Polar covalent. How about these two? Some pretty tough math here. What about those two? Chloe, what do you think? Non-polar. 2.2 minus 2.2. Last time I looked, it's going to give me 0. What about these? Oh, don't tell me you're doing that math. Minus 1. What is it? 2.16. Okay? Where does the 2.16 fall? Into an ionic bond. Okay? Here's a good one. Here's a good one to talk about. Go ahead and do the math here, and then we're going to discuss this 1 second. Okay? 3.16. 1.61. What do you get? What do you get? 1.55. All right? So you're telling me that that would be what type of a bond? Carly, what type of a bond? A polar covalent bond. But that one's between a metal and a non-metal, isn't it? Because didn't we say aluminum was a metal? Okay. But yet our numbers tell us that it is more of a polar covalent than what it is in an ionic. All right? Now, let's look at our little chart there. We said 1.55. What's the ionic character? What's our ionic character of that aluminum and chlorine bond? Okay? Somewhere between what, 43 and 47? Okay? 43, 47, let's say 45% ionic character. It's about midway between those two, right? So about 45% ionic character. So it doesn't quite make the numbers to be an ionic bond. Okay? Here's magnesium and oxygen. What do you think? Magnesium and oxygen gives us 2.13. Okay? So where does that fall? That falls into an ionic, correct? All right. Now, here's just another way. I showed you these partials. The partial, the partial. Okay? We said that chlorine was 3.16, hydrogen was 2.2. So we knew that this was a polar covalent bond. So this is partially negative, partially positive. Here's another way we can write it. We can have a plus sign here with an arrow pointing to the negative side. So the plus side with the arrow pointing to the negative side. And once again, the partials. So these electrons are pulled more to the chlorine than they are to the hydrogen. And remember, we're only talking about this shared pair of electrons, not the unshared pair, the shared pair of electrons. Now, let's talk about polar molecules. Those are polar bonds. Let's talk about polar molecules. Well, what's the difference? Okay, what's the difference? Well, a polar molecule would have a positive and a negative end. We need to have two things in order to have a polar molecule. First, we must have polar bonds. Second, we need to have an asymmetrical molecule. What's that mean? What's asymmetrical? Not symmetrical. A is not. So a molecule that is not symmetrical. Well, what does that mean? Okay? What does that mean? Well, here, I look at hydrogen and fluorine. We've been talking about this. We know that that is a polar molecule. We know it's a molecule because they're bonded together. There's only two of them. So the electrons are being pulled to the fluorine. Now, if you look, hydrogen, oxygen. What's oxygen's? 3.44. Okay, minus the 2.2. Okay, so 3.44 minus the 2.2. That's going to give you what, 1.24? Am I doing my math right? Okay, so that falls into the polar. But look, this is what we call asymmetrical. Okay, now look at this one. These are all four polar bonds. Okay, Chlorine's a 3.16, carbon's a 2.55, I believe. Okay, does that sound right? 2.55? Yep. So we have 4 polar bonds here. But this is a symmetrical molecule. Okay? If you look, all 4 of the chlorines are pulling the electrons towards them, right? So the net pull is going to cancel everything out because of the symmetry. So it must have polar bonds, number 1, and it must be asymmetrical molecule in order to be a polar molecule. Now, let's look at some of these, okay? These are, we just looked at carbon tetrachloride right there. Here's carbon dioxide, okay? Here's carbon dioxide, and here's borane trifluoride, okay? If you look at carbon dioxide, it's a double bond. It's a double bond. The oxygens are winning the tug of war. But due to the symmetry, both oxygens are pulling on the carbon the same amount, so nobody's winning the total tug of war. Okay? We talked about the carbon tetrachloride in the last one. Look at how the boron trifluoride bonds. Okay? Once again, the fluorines are all winning the tug of war. They're all pulling out towards the electrons, out towards them, but no net movement is occurring. Now here are the asymmetrical ones. Okay? We can see that this oxygen is pulling these electrons and these electrons. So based on the lack of symmetry, okay, here is the nitrogen. Okay, this is actually ammonia. Okay, this is actually ammonia. We could call it nitrogen trihydride, but it's actually ammonia. We can look. The nitrogen pulls all 3 of these electrons, all 3 of these electron pairs towards it. And we talked about that one already. The final thing we're going to talk about today is about dipoles. Okay? And we've really already talked to them. We've already talked to them. We've already talked about them. Okay? Unequal sharing of electrons is where we have 2 regions that are polar, 2 poles. All right? We talked about a dipole. This is actually the word we give. Okay? The word we give here, the dipole for this. So having a negative and a positive region. I look at this. I say, okay, once again, here's carbon dioxide. Carbon is partially positive, oxygen's partially negative. Partially positive, partially negative. So if we look at this bond, the electrons are being pulled to the oxygen. If we look at this double bond, the electrons are pulled closer to the oxygen. But the overall polarity cancels. Not the case here. We see the dipoles here. Okay, the electrons are being pulled to the oxygen with that bond. The electrons are being pulled to the oxygen. So the net polarity is this side, this lower part of the water is going to be partially positive. This higher part's going to be partially negative. So as we look at this, and these things right here, we'll learn next week. Okay? We're going to be talking about these things next week, molecular geometry, the shape that these particular molecules take. All right? So we look at the bond. We have a polar covalent bond here. We have the molecule with its shape, a polar molecule. Okay? Here is a nonpolar covalent bond. I don't know about that one right there. What's the math here? 2.55 minus 2.2. That's a 0.35, right? So I would say this diagram is wrong because we would classify that as polar, wouldn't we? Are my numbers right? 3.55 and, wait, 2.55, right? 2.55 and 2.2, so it'd be 0.35. So we would classify that as a polar covalent bond. So we would classify this as a polar covalent bond, but yet the molecule would be nonpolar. Okay. I don't think we need to practice drawing dipoles, do we? Can we tell? Do we need? Can we do this without practice? Can we tell that? Here, the bromine's 2.8, the phosphorus is 2.1. That gives me a 0.7. So I do have a polar covalent bond. Can you tell which side's the positive one? The one with the lower electronegativity. I don't think we need to practice that. I think we could be okay without doing those. Okay. Now let's look at these. Okay. Look at these and say, all right, is this a polar molecule? How I like to do these, folks, is I like to think and relate them to what I know. This HF right there looks a lot like HCl, doesn't it? Okay, HF is a lot like HCl. I know that fluorine's 3.98. Okay, I know that hydrogen's 2.2. What does that fall under? 398 divided or minus 2.2, 1.78. That gives me the gray area, right? Do I have a metal? No, hydrogen's not a metal. It's a gas. So I look at that and I say, okay, hydrogen fluoride's going to be a polar molecule. I already know about water. I know about ammonia. I don't know why I put those in there. I even know about carbon dioxide. Let's look at this one. CF3. What does that look like? 4. Okay, CF4. What does that look like? What one have we been talking about? Nobody knows? How about CCl4? Haven't we been dealing with that? Didn't you look at that just a little while ago? Can you remember that all the way back to 5 minutes ago or not? Okay, what was that? What was that? The fluorine obviously is going to win the pull. So if I would draw this, and I'd have carbon, and I'd have a fluorine here, a fluorine here, a fluorine here, a fluorine here. Is that asymmetrical? No, it's not. So do you think that that will be a polar molecule? No, it will not. Okay? No, it will not. So, in polar bonds, we have one atom that has more electronegativity. Okay? In nonpolars, they are the same. If it's asymmetrical with polar bonds, we have polar molecules. If it's symmetrical with polar bonds, we have nonpolar molecules. Okay? Any questions for me about polarity?